Hello and welcome back. In this video, we are going to study an important data structure called Disjoint Union data structure. So without wasting time, let's get into the details. So in this video, we are going to study a data structure called Disjoint Union data structure. So here we are given a universal set, finite set without loss of generality. We can assume that it has n elements, and the elements in the universal set are 0, 1, 2 up to n minus 1. So we want to make a set with initially we have all single cell sets, that is for every I we have a set containing exactly one element. So this can be done in order n. Then we have two important operations to be done on these sets. At any point of time, what we have is the disjoint collection of disjoint subsets of this universal set. So given two elements, disjoint of I comma j, we want to know whether I and j belongs to the same set or a different set. Okay. And in the union of I comma j, if you give me I and j which belongs to the two different sets, then we want to replace the set containing I and set containing j with the union of these two sets. Going back to the example of Kruskal's algorithm, the set is collection, essentially the set of nodes. Make set is essentially you take all the nodes and without any edges, all isolated vertices. This is our initial MS tree that we have. So given an edge, I want to know whether the endpoint belongs to the same set or a different set. In other words, all the elements at any point of time which are in the same connected component, they will be in one set. So if I give you an edge and ask the question whether they are disjoint, that means that it's equivalent to asking the question whether they are in the same set or a different set. If they are in the same connected component, then they are in the same set. If they are in two different connected components, it's in the two different connected components. Now it's easy to see that the union is actually, if the elements are two different sets, that means that they are in two different connected components. Finding the union of two elements is exactly equal to finding the adding this edge and merging the two connected components. So for time being, we'll just stick to the example of sets. Initially we have all isolated sets. At any point of time, we'll either merge two sets or given two elements, we want to know these two elements are in the same set or different sets. For example, if I have the set A which contains 1, 3, 5, set B contains 2 and 7, and set 3 contains 4 and 6. If I give you disjoint 4, 5, that means that they are in different sets. 4 is in set 3, set C, and 5 is in set A, so they are in different sets. If I give you 3, 5, then both 3 and 5 are in the same set. Now if I want you to merge B and C, I might give you union 2, 4. If I give you 2, 4, the set containing 2 is B, set containing 4 is C, so you should replace the B and C with one set which contains B union C. Let's look at an example, a concrete example how this actually happens. We have the set 0, 1, 2, 3 and 4. So initially I have something called a color which will tell you all the elements in the same set will have a same color, and at any point of time I'll ensure that elements in the different set will have different color. Okay, so this will help me to answer the disjoint question. Given two elements, I just look at the color of two elements. If they are same, that means that they are in the same set, and if they are in the different set, the colors will be different. So when I want to find the union of 1 and 2, that is right now all the single cell sets are there. The color of I is I itself. So when I want to find the union of 1 and 2, I want to so the set 1 containing 1, set containing 2 should be merged, and these two sets should be replaced with a set containing 1, 2. So after I find the union of those two sets, both the elements should have the same color. So what I do is that I change the color of 2 to 1. When I want to find the union of 3, 4, I go back and change the color of 4 to 3. So after I do these two mergers, so I have three sets, set containing just 0, set containing 1 and 2, set containing 3 and 4. The set containing 1 and 2, all the elements have color 1, set containing 3 and 4, all the elements have color 3. Now if you want to ask me the question whether the 1 and 4 are disjoint, answer is yes, because the color of 1 is 1, color of 4 is 3. The 1 and 4 are in two different sets. But if you ask me 3, 4, they are in the same set because color of both of them is 3. Now if you want to find the union of 0, 2, so set element 0 has color 0, say The element 2 has color 1, so they are obviously in the two different sets. Now one option is to change the color of 0 to 1, so that when I find the union of these two sides, 0, 1 and 2 will be in one side. So one option is to change the color of 0 to 1 or change the color of 1 and 2 to 0. But we want to do minimum color changes. What I do is that I take the element when I want to merge two sides. What I need to do is that I take the smaller side and merge with the bigger side. So I change the color of the smaller side to the color of the bigger side. So I take the color to the element 0 and change the color to 1. So after I merge 0 and 1 and 2, so I have two sets now. The one set containing 0, 1 and 2, color of all the elements is 1. The other set that I have is 3, 4, and the color of both the elements is 3. Remember, the coloring is given in such a way that elements in the same set have the same color. Elements in two different sets will have different colors. And at any point of time, the union of all the sets that I have is exactly equal to the universal set, and these sets are all disjoint sets at any point of time. So when I want to find the, now if we ask me 1, 4, so they are in two different sets because color of 1 is 1 and color of 4 is 3. But if you want to ask me whether disjoint of 0 and 1, then I will say that both of them 0 and 1 are in the same set because color of both of them is 1. Now if you want to find the union of 0, 4, the color of 0 is 1, color of 4 is 3, but there are only two elements which color 3, but there are three elements which color 1. So what I do is that I take the side which has the color 3 and change all the colors to 1. So when I perform that operation, this is the set that I get. So you have one side which is the universal set which contains all the 5 elements. So if I have to implement this algorithm, so what I need is, given a I which is an element, C of I, the color of the element, the set to which the element actually belongs to, the color of the set to which the element actually belongs to. S of C of I is the number of elements in the set whose color is C of I. List of C of I is the list of all elements in the set whose color is whose color is C of I. For example, if I go back to the previous example, here, so if you ask me C of 3, it's 3, C of 1 is 1, and S of 1 is 3 because there are 3 elements whose color is 1. S of 3 is 2, S of 2 is 0 because there is no element whose color is 2. The list of 1 will contain the linked list containing 0, 1, 2. List of 3 will contain the list containing 3, 4. So when you do the make set, it's easy. You set C of I is equal to I. When you list of I, with this will have only one node. Create a node and add it to the list of I. S of I, size of I is exactly equal to 1 because there is only one number whose color is 1. So now when you want to find the disjoint I, j, given two elements, I want to know whether they are in the same set or different set. If elements I, j belong to the same set, if and only if C of I is exactly equal to C of j. This is easy to see. Elements in the same set will have the same color. Elements in the different set, the coloring will ensure that they will be in the two different sets. This disjoint can be answered in order 1. So now let's look at the union operation. So when I want to find the union of I, j, I take the smaller set and merge it with the bigger set. So the size of C of I is smaller than the size of C of j. So if this is not the case, I will swap I and j. In that case, the ith set containing I will be merged with the set containing j. So S of C of I will become 0. Before that, I have to update my S of C of j plus is equal to S of C of j plus S of C of I. So all the elements containing I will be merged with the element containing with the set j. So after you do the delete each element in the list C of j because there will be no list of C of j, and add this to the list C of j, and change the color of each of the element in C of I to C of j. So this is called merging a smaller set with a bigger set. So what you do is that you delete all the elements in the list of CFI and add it to the list CFJ and change every element whose color is CFI. Okay, how do you get every element in whose color is CFI? The list of CFI will give you that, right? To delete every element from CFI and add it to the list of CFJ, and when you do that, change the color of CFI to change each node element from CFI to CFJ. So this in worst case can become n by 2, because when you want to merge two sets, both of them could have the same color. So what you end up doing is that each linked list has n by 2, n by 2. You want to go and look at a smaller set and change the color of all of them and add it to the other list. This can take n by 2 amount of time, right? In worst case, one union can take order n time. So, but this doesn't happen quite often. So what we are going to show is that we shall show that n unions put together will take n log n time. So instead of asking how many color changes that we are doing, so the number of color changes that we are doing is exactly the total complexity of n unions. Every time when you do a union, so you're going to change the color of smaller set into color of bigger set and take that element from the list of CFI and add it to list of CFJ. If I can figure out or keep track of how many number of times each of the element undergoes color changes, then n into the number of elements will be the total complexity of the union operation. So what we are going to show is that each element can undergo changes color at most n number of log of n number of times. Let's look at the quickly proof of this. So what we are going to, so this is an important theorem. If an element has changed its color k number of times, then the size of the set to which it actually belongs to should be greater than or equal to 2 to the power k. So as and when you change the color of an element, the size of the set to which it belongs to grows exponentially. That's what this theorem says. It's easy to see, that means the size of CFI is greater than or equal to, from our notation, is greater than 2 to the power k. The proof is by induction. If k is 0, that means that you have not changed the color of any of the element. So the size of the set to which actually belongs to is 2 to the power 0, which is equal to 1, right? So each set in the beginning has exactly one element, singles and sets. Okay. So now when you when an element has changed its color kth time, it has already changed its color k minus 1 time. And let's look at the kth color change. Since the element has already gone into k minus 1 color changes before I did the kth color change, the size of the set to which it actually belongs to should be at least 2 to the power k minus 1 by induction. But when you merge this set with a bigger set, you are always going to merge a smaller set with a bigger set. So when you merge a smaller set with the bigger set, the elements which are in the bigger set, their colors don't change. Only elements in the smaller set, their colors will change. So every time a smaller set will be merged with a bigger set. So after you do the color change, the set to which it actually belongs to is 2 to the power k minus 1. This is the actual set, and it's merged with a bigger set. Since this set itself has 2 to the power k minus 1 elements, any set which is bigger than this with which it has been merged will have at least 2 to the power k minus 1 elements. When you add this up, you get 2 to the power k. So the important theorem that we get is that if an element has changed its color k times, then the size of the set to which it actually belongs to should be at least 2 to the power k. But the size of the universal set is only n. So each number can only undergo color changes log n number of times. So if I do n unions, it will take at most order n into log of n. So in summary, the make set which is initializing our MST will take order n. So the disjoint is asking the question whether to given an edge in the decreasing order of the finish time, I take the edge and ask the question whether they are in the same connected component or not, which is equivalent to ask the question whether they are in the same set or not. The elements, the nodes in the same connected component are represented by a set here. If an edge goes across the connected component, these two set elements should belong to two different sets. If the edge goes within the same connected component, that means that these two elements are in the same set. So there will be, if the disjoint operation is easy now, this will take only order one time because I have to just look at the color of CFI with color of CFG. But the union, we have said that if you do n unions, the total complexity of this algorithm is log of n. Okay, so Kruskal's algorithm makes n calls to the disjoint function. You take all the edges one by one and ask the question whether they belong to the same set or a different set. Only when they belong to a different set, you end up merging these two. So you started with all n, singleton sets, and after n unions, you will certainly have only one set. So the maximum number of unions that you're going to do is n minus 1. So the cost of all the disjoint calls is order m, and all the calls to the union is n minus order n into n minus 1. So the total complexity of Kruskal is m into n log n. This is for sorting the edges in the increasing order the weights, and order m is for all the disjoint queries that I do. N log n is the total complexity of all the unions. So the Kruskal's algorithm, by using this method, can be implemented in order n plus m log of n. So in the next class, we're going to see how to implement. So right now what we have done is the disjoint was order 1, but the union was log of n on average. Okay, so n unions took n log n. So on average each union take log of n time. So what we are going to do in the next class is that we can do union in order 1, but the disjoint will be order 1 amortized cost. So if you do n number of calls to disjoint and m minus 1 calls to the union, then so the total amount of time that you will end up spending is only order n plus m. Okay, so the first part of the Kruskal will still take m into log of n for sorting, but this disjoint union query can be answered in order m plus n. So the summary is that right now we are able to do disjoint in order 1, but the union in on average log of n. But in the next class we are going to see how to do disjoint in order 1 amortized, but the union in order 1 in worst case. So in this video we have defined what is the disjoint union data structure. It's a data structure on which we want to do two different operations, maintaining disjoint subsets of an universal set. So one of the operation was disjoint, given two elements. We want to know whether these two elements belong to the same set or two different sets. And the union was, if I give you two elements which belong to two different sets, we wanted to find the union of, replace the original sets with the union of two of the sets. So we have seen an implementation of the data structure which will enable us to do disjoint in order 1, but the union, n unions in n log n. In other words, each union was taking order log n. In the next class, we'll come back to the same problem. We will discuss a way of implementing both union and disjoint in order 1.